Okay. Today we will discuss some problems based on the linear transformations. Okay. Here, uh, here we today our topic is projection. Right. First, want to understand what is the projection. Then we can do some problems based on this projection. Okay. Right. Projection means the projection based on the topic you can note it. Projection means we consider the direct sum. You already know that direct sum be equal to W1 direct sum W2. Okay, W1 direct sum W2. You can find such element alpha belong to B, right? Alpha belong to B. There is unique expression. There is unique expression alpha equal to alpha 1 plus alpha 2, where is alpha 1 belong to this W1 and alpha 2 belong to W2. Okay, alpha 2 belong to W2. The projection, the projection, the projection on W1 along W2, right? Along W2 is the linear transformation. Is the linear transformation, right? The linear transformation, right? Is the linear transformation, right? Is a linear transformation E on B, right? On B defined, right? Defined by this formula very important. E power, sorry, E alpha, its function E alpha equal your alpha 1, like here alpha 1. E alpha equal alpha 1, right? It is your projection. Okay, it is your projection. Okay, it is your projection. Right. Today, we will discuss some problems projection. Right. Every time I will tell, right, in these questions what the projection, we use the projection condition, we use the projected condition like that. Okay. Hey, our condition is projection. Okay. We do some problems based on this projection. Okay. Okay. First problem, a linear transformation, exercise 1, a linear, right, a linear transformation E linear transformation E, right, a linear transformation E, okay, a linear transformation E, uh, right, a linear transformation E, a linear transformation E on B, E on B, E on B, E on B is a projection, is a projection, is a projection on some subspace, right, on some subspace, right, on some subspace, right. B is the projection on some subspace, okay, on some subspace, right, subspace, if and only if and only if it is idempotent. Right? So this idempotent means, right? First you understand this idempotent means, right? Idempotent means E squared equal E, right? This E squared equal this formula, right? For idempotent, you also E squared equal E, right? a new word for you, right? Item. Right, okay. This you want to prove this this statement. Okay, you want to prove this statement first, right? First, suppose that suppose that okay, suppose that uh, you can write B equal to W1 direct sum of W2. Okay, W1 direct sum of W2, and let E be the projection W1 along W2. E be the projection on W1 along W2. Okay, W1 along W2. Therefore, your claim, or otherwise you can write, we shall prove that squared equal E. Okay, E squared equal E. First, let alpha belong to B, one of the vector, right, in B. Then you already know that alpha equal alpha 1 plus alpha 2, because B equal to direct sum of W1 W2, where alpha 1 belong to W1 and alpha 2 belong to W2. Okay, alpha 2 belong to W2. We have, by definition of, right, by definition of the projection, we have e power e alpha equal alpha 1. Okay, now we can take both side e, then e alpha. You know, this means e squared alpha, no? This means e squared alpha, e power alpha, e alpha 1, right? E alpha 1. You can write this one as a e alpha 1 plus 0. You alpha 2 now 0. Okay, alpha 1 plus 0. In this case, alpha 1 belong to W1 and 0 belong to W2, because here W1, W2 are subspace. Therefore, 0 W2 subspace, no? 0 belong to W2. Okay. Now you have the definition for the e power alpha 1 for the projection dimension, right? For any values of alpha, e power alpha equal alpha 1. Therefore, this value is equal to alpha 1. Alpha 1, you already know that by the projection e power alpha. Therefore, for any values, alpha is arbitrary one of the vector. Therefore, the result is true for all values in B. Therefore, E squared equal E. Therefore, E squared equal E for all alpha belong to B. Therefore, E squared equal E for all alpha belong to B. If this is a necessary part, and sufficient parts also you want to prove that, right? This part now we prove here. Now for the converse part, the sufficient part, you want to prove it. What's the thing you want to prove it? Suppose it is item potential E squared equal E, then you want to prove that E on B is a projection on some subspace. Therefore, you want to prove that E is a projection. Therefore, what is the meaning of projection? You want to prove that, right? This condition, E of alpha equal alpha 1, you want to prove that. Okay. Now we will try to prove that converse part. Right? We will try to prove the converse part. Conversely, suppose that right? Conversely, suppose that you assume that E squared equal E. Is it okay? Yes. E squared equal E. Now we define the two sets first. W1 one of the set. W1 take the values alpha belong to B. Your condition is E power alpha. Sorry, E alpha equal alpha. It is your W1 set. W2 another set. We define two sets. Okay. Alpha belong to B. Well defined. Okay. E alpha 0. Obviously both are well defined, right? Or the del well defined, right? Right. For this part, a linear transformation E on B is a projection on some subspace. For that, right, for that, first you want to show that both are subspaces. Okay, first you want to show that both are subspaces. That is your first condition. Obviously, this one is a subspace because you already know that. Suppose it is a null space. No, it is a null space. Null space is a subset of W1. So obviously true, right? Therefore, W2 is a subspace, right? W2 is a subspace of B because it's a null space, no? Null space of E. Null space of E. Now, you want to show that W1 also subspace of B. For that one, also, now your claim is you want to show that we shall show that W1 is a subspace of B. Okay, W1 is a subspace of B. Therefore, how can you show the subspace? Let you take two vectors alpha comma beta belong to W1. There are two vectors, okay? Alpha comma beta belong to W1. There are two scalar. You take A comma B are scalars field F. Okay. Now, alpha comma beta belong to W1 means this one belong to this element. Therefore, satisfying there e power alpha equal alpha and e power beta equal beta. Now you consider this part e power alpha, sorry, a alpha b beta. E is a linear transformation. Okay, E is a linear transformation. Therefore, you will write a power e alpha b power e beta. This is your a alpha b beta. So therefore, e power a alpha plus b beta equal a alpha plus b beta means yeah, both are same. Both are same. That means this is the element of W. But alpha, sorry, a alpha b beta element of W1. Therefore, it is a subspace condition satisfying. Therefore, W1 is a subspace. Right? W1 is a subspace. Now we want to prove that E is the first part okay, subspace okay. Now we want to prove that E is a projection mapping. Okay, E is the projection, right? Now we shall prove that E is the projection on W1 along W2. As claim, you want to prove that E is a projection along W1 along W2. Okay. Now we shall prove that. Okay. Now we shall prove that. Now we shall prove that E is the projection on W1 along W2. This part now we want to prove is the projection along projection on W1 along W2. Okay, is the projection on W1 along W2, right? You already know that. What is the definition for the projection mapping? You want to show that e power alpha equal to alpha 1, right? This you are claim now. Right. For the projection curve parts, you want to show that you already know that for beginning of the definition, first you want to show that these things, the direct sum condition also important for the projection. First condition you want to show that B equal to W1 plus W2. Right. The direct sum means you have to show that two things. First, this addition terms. Second one, this W1 intersection W2 singleton 0. These are the things. It is suppose these two things are satisfying, you can say that V equal to W1 direct sum of W2. Okay, two things are satisfying, we can say that W1 direct sum of W2. Okay, now we want to show that these two things are satisfying. Then only you can define the projection mapping. Okay. Okay, first part. For first part, let you take arbitrary one of the element vector alpha belong to V. Then alpha, right? Alpha, we take alpha equal to E alpha plus, is it okay? It's 2 are cancelled, we can get alpha. Let you take this one, E alpha is alpha 1 you are E alpha, and alpha 2 you are alpha minus E alpha. Therefore, we use these two things, you will get alpha equal alpha 1 plus alpha 2. Now is the linear transformation. Therefore, you take both sides E. Otherwise, using this part first. Using this part first. You have this part, no? This part. You take E both sides, E power alpha 1 into E alpha. E alpha means E squared alpha. E squared alpha, use the assumption E squared equal E. Therefore, E squared equal E alpha. We already know that E alpha, right? E alpha, right? E alpha equal to alpha 1. E alpha equal to alpha 1. Okay. Now we have E alpha 1 equal alpha 1. Here, E alpha 1 equal alpha 1 means alpha 1 belong to W1. Therefore, alpha 1 belong to W1. Right? Alpha 1 belong to W1. Now we want to show that alpha 2 belong to W2. Okay. Alpha 2 belong to W2. We want to show that. Next. Therefore, you consider this one, E power alpha minus E alpha. Okay. This part. That means you can write like this, right? E power alpha 2, okay. E power alpha 2 means E is a linear transformation, then you will write E power alpha. Then you have E is a linear transformation, E power alpha minus E squared alpha. Okay, E squared alpha is from our assumption E squared E. Then this one E alpha, this one E alpha, we will get 0. Therefore, E alpha to 0 means alpha 2 belong to W2, right? Alpha 2 belong to W2. Alpha 2 belong to W2. Thus, we will write, we already have alpha belong to V, no? Alpha belong to V. We will write alpha equal alpha 1 plus alpha 2, right? Alpha 1 plus alpha 2, right? Alpha 1 plus alpha 2, okay? Alpha 1 plus alpha 2. Therefore, here alpha 1 belong to W1 and alpha 2 belong to W2, right? Alpha 2 belong to W2. Therefore, alpha belong to B, no? B element of alpha belong to B. B equal alpha 1 belong to W1 plus alpha 2 belong to W2. Right? Alpha 2 belong to W2. Okay? Alpha 2 belong to W2. Alpha 2 belong to W2. Now we want to show that this W1 intersection W2 singleton 0. Next part. Right. Let alpha belong to W1 intersection W2. Then you take this alpha, one of the element alpha belong to W1 intersection W2. Now we want to show that alpha equal to 0. Therefore, alpha belong to W1 and alpha 2, so alpha belong to W2. Right? Now alpha belong to W1. Alpha belong to W1 means the condition is e power alpha, sorry, E alpha equal alpha. Also, alpha belong to W2, we have the condition, and alpha belong to W2, we have the condition, e power alpha becomes 0. Both are same, therefore, e power alpha equal alpha, that one equal to 0. Therefore, alpha 0, no? Therefore, W1 intersection W2, there is no element singleton 0. These two conditions are satisfying, then you can say that therefore B is the direct sum of W1, W2, right? Direct sum of W1, W2. Therefore, our direct sum condition okay. Then now you can define the projection map, right? For the projection map, you want to show that e power alpha equal to, here alpha 1 belong to W1, alpha 2 belong to W2 now. Therefore, you want to show that e power alpha equal to alpha 1. That is your projection mapping, right? Now, now now let this alpha 1 belong to W1, alpha 2 belong to W2. You want to show that e power alpha equal alpha 1. Okay, e power alpha equal to alpha 1 plus alpha 2, right? Is sorry, this is a linear. Therefore, e power alpha 1, e power alpha 2, e into alpha 2. E in alpha 1 means alpha 1 belong to W1 means e power sorry, e alpha 1 equal alpha 1 plus this one 0. You get alpha 1. If that is E alpha equal alpha 1. E alpha equal alpha 1 means it is a projection mapping condition, right? Hence, E is the projection along W1 along W2 is projection on W1 along W2, right? W1 along W2. Is it okay? W1 along W2. Okay, W1 along W2. Next part. Next part. Let next part. Let next part. Next exercise 2. Exercise 2. Suppose that the vector space B is the direct sum of is the direct sum of its subspace W1 and W2. If E is the projection on W1 along W2, if E is the projection on W1 along W2, then you want to show that then W1 and W2 are respectively the set of all solution of the equations. W1 and W2 are respectively the set of all solution of the equations, right? The equations are this one: e power alpha equal a and e power alpha equal 0. For this proof, right, right, let for the solution you take let B be the vector space. You take let M is the alpha belong to B, here E alpha equal A, and N another vector, so N another set of another set alpha belong to B, E alpha 0. Now you want to prove that here W1 and W2 are respectively the set of all solution of this one. We consider for this set for the W1, we consider this set for the W2. Therefore, you want to show that, right? Your claim is, there are two claims there. First claim, you want to show that M equal to W1 and N equal to W2. These are your claims. N equal to W2. M equal to W1 means you want to show that M subset of W1 and W1 subset of M. Similarly, N subset of W2 and W2 subset of N. These are things you want to show that for this part. It is the question. Now we will try to do the first part. You take one of the arbitrary element, let alpha belong to W1. Right? Let alpha belong to W1. Okay? Let alpha belong to W1. Let alpha belong to W1. then this alpha belong to V, right? And it can be written as, right, written as, you can write alpha equal alpha plus 0. You already know that alpha 1, alpha 2, like alpha 1, alpha 2, therefore this where alpha 1 belong to W1 and 0 belong to W2. Now we use the projection definition. By projection definition, we have e power alpha, right? E power alpha, right? Projection definition e power alpha. This e power alpha, your value is a, no? Your value is a. It is take a. Suppose e power alpha equal a means, right? E power alpha equal a means now your alpha, right? This condition satisfying. E power alpha condition satisfying. Therefore, this alpha belong to M. Therefore, from this one we will write, right? From this one we will write here alpha equal alpha plus 0, then e power alpha equal a by the projection mapping. Therefore, e power alpha equal a means this alpha belong to M. Therefore, this alpha belong to M. Therefore, alpha belong to W1, alpha belong to M. Therefore, W1 subset of M. Now, let you take alpha belong to M. Then our condition e power alpha, right? E power alpha belong to M means e power alpha, right? E power alpha, take the value. What is the value? We take here. Here we assume that here let your alpha, no, this one alpha plus 1, alpha 2. Here alpha 1 belong to W1 and alpha 2 belong to W2. E power alpha equal alpha 1, no? Alpha 1. A is one of the number, right? Like here, you take e power alpha equal alpha 1, right? E power alpha equal alpha 1. Therefore, now we take this e power alpha here for this equation, e power alpha 1 plus alpha 2, or define this e power alpha 1 equal alpha 1. Now we here alpha belong to M. Can I assume that here alpha? Yes, alpha, e power alpha also possible, no? E power alpha, A mean any vector values, right? Alpha also possible, right? Therefore, e power alpha, suppose you assume that e power alpha, then this one is alpha. Alpha already know that alpha belong to which one? Right, alpha 1, right? Alpha 1 belong to which one? W1. Therefore, alpha also belong to W1. Therefore, M subset of W1. Second one, first one, both implies 1 and 2 implies M equal W1, right? M equal W1. Okay, M equal W1. Now you want to show that N equal W2. N equal W2. For that, let alpha belong to W2. Then alpha belong to V, no? Then alpha belong to V. Alpha belong to V, right? Can be written as alpha equal 0 plus alpha. Is it okay? For all, right? For here, 0 belong to W1 and alpha belong to W2. 0 belong to W1 and alpha belong to W2. Can be written as that form. 0 belong to W1 and alpha belong to W2. Okay. 0 belong to W1 and alpha belong to W2. Okay. Alpha belong to W2. By the projection, by definition of projection, we have e power alpha. E power alpha definition 0. Definition e power alpha 1, there is no alpha 1. Alpha 1 equals 0 now. Therefore, e power alpha 0. Okay, e power alpha 0. E power alpha 0 means this alpha belongs to n, one of the element n. We assume that alpha belongs to W2. We prove alpha belongs to n, therefore W2 subset of n. It is your first condition. Now let you take alpha belong to n. Then alpha belong to n means we have the condition e power alpha should be 0. E power alpha should be 0. Let alpha equal alpha 1 plus alpha 2, where alpha 1 belong to W1 and alpha 2 belong to W2. We have by the projection e power alpha equal to alpha 1, no? E power alpha equal to alpha 1. But we have e power alpha 0, alpha 1, therefore alpha 1 0. Right? Alpha 1 0 means only you have alpha equal to alpha 2. Alpha 2 belong to W2, therefore alpha also belong to W2. We have alpha belong to n, and we prove alpha belong to W2, therefore n subset of W2. Second one, right, 1 and 2 implies n equal W2, right? N equal W2. Is it okay? N equal W2. These are the things, right? To do these questions. Okay. Next questions. Now next question. Now next question. Next question. This exercise 3. Suppose the vector space B is the direct sum of its subspace W1 and W2. Suppose the vector space B, right, vector space B is the direct sum of its subspaces W1 and W2. Its subspaces W1 and W2. If E is the projection, on W1 along W2, then first part, the range of E, right? The range of the range of E, that is your range of E equal to W1. The null space of E, the null space of E, null space of E, that is null space of, you can denote by N E, okay, is W2. N equal is null space, okay, N E. Otherwise, you can denote this one as a null of E equal W2. Is it okay? Null of E equal W2. This part now we want to prove. First, range of E. Alpha belong to B. Alpha equal E power beta. Is it okay? For some beta belong to B. For some beta belong to B. For some beta belong to B. Now you want to show that this condition R of E equal W1. Okay, R of E equal W1. Let alpha belong to W1. Then alpha equal alpha plus 0. Is it okay? Where alpha belong to W1 and 0 belong to W2. Okay, 0 belong to W2. Therefore, you have e power alpha, this one alpha, right? E power alpha is an alpha. Suppose e power alpha, alpha mean, right, this alpha belong to range of E. We assume that first alpha belong to W1, and we prove that alpha belong to RE, therefore range of E, alpha W1 subset of this one. W1 subset of this one first. W1 subset of this one. Now you want to take the element from this range of E. Let alpha belong to range of E. Then there exists another alpha belong to B, right? Another alpha belong. There exists beta belong to B. Beta belong to B such that e power beta equal alpha. E power beta equal alpha. Now you can take these terms. E power right, this one means E squared, no? This E squared beta, E power alpha. Previous exercise we prove this item button E squared equal E beta, therefore, right? This E beta equal E alpha, but E beta equal alpha equal E alpha. Therefore, E alpha equal alpha means this alpha belong to W1, right? In the previous part, you already know that what is a W1 set, what is a W2 test. Therefore, alpha belong to W2, sorry, W1. Therefore, alpha belong to range of P, alpha belong to W1. Therefore, range of E subset of W1. This is your second condition. 1 and 2 implies range of E equal W1, right? Range of E equal W1. Second part, you want to show that null of E equal W2. Null of E equal W2. For that, you want to show that it is your condition, second part. N of E means alpha belong to B, right? E power alpha 0. It is your condition for W2, right? You take, let alpha belong to W2. Alpha belong to W2, then alpha belong to B can be written as right, can be written as alpha equal 0 plus alpha, where 0 belong to alpha, sorry, W1, and alpha belong to W2. Alpha belong to W2, right? By the projection definition we have here, what is the E alpha? Alpha 1, no, here alpha 1, 0. Right? Alpha 1, 0. Therefore, E power alpha 0 means alpha belong to null of this E. Right? Null of E. We assume that here alpha belong to W2. We prove that alpha belong to N of null of E. Therefore, this W2 subset of N of E. First one. W2 subset of N of E. Let alpha belong to null of E. Then by the definition we have E power alpha, sorry, E alpha 0. Let alpha equal alpha 1 plus alpha 2, where alpha 1 belong to W1 and alpha 2 belong to W2. Okay, alpha 2 belong to W2. Therefore, e power alpha equal to alpha 1 by the projection mapping, but e power alpha already 0 equal alpha 1, therefore alpha 1 0. Alpha 1 0 means alpha equal only alpha 2. Alpha 2 belong to W2. We assume that here alpha belong to null of E. We prove that alpha belong to W2. Therefore, this null of E subset of W2. It is your second condition. 1 and 2 implies we will prove it's null of E set W2. Okay, null of E set W2. Okay. Next exercise. Next exercise. Next exercise. A linear transformation E is a projection. A linear transformation E is a projection. If and only if you want to show that I minus E is projection. If E is the projection on W1 along W2, if E is the projection W1 along W2, then I minus E is the projection on W2 along W1. I minus E is the projection on W2 along W1. suppose that E is the projection. E is the projection means we already proved so idempotent E squared equal E. Now we want to show that I minus E is projection. That means you want to show that I minus E is a projection means, right? I minus B will projection if I minus E squared equal I minus E. I minus E squared equal I minus E. Okay. I minus E squared equal I minus E. Okay, now we will do that part. You consider this part I minus E squared. I minus E. I minus E. I minus E plus E squared. But we have E equal E squared. Therefore, right, I minus E squared E plus E cancel, we get I minus E. Right? I minus E. Therefore, I minus E squared equal I minus E means I minus E is a projection. Right? I minus E is the projection. Converse part, suppose I minus E is the projection, you want to show that E is the projection. That means converse part, you take this I minus E squared equal I minus E, you want to show that E squared equal E. Conversely, suppose that right? Conversely, suppose that I minus E be the projection. That is I minus E squared equal I minus E. Now, from this condition, I minus E. Now, what is the value? I, E minus E squared, I minus E. Now, right, from this part, I is cancel, minus E cancel. From this part, we will get E squared equal E. E squared equal E means E is a projection. Right, using previous part is the projection. Now, you want to show that here E is the projection from W1 to W2. Then you want to prove that. Another furthermore parts. E is the projection W1 along W2. We assume that you want to prove that then I minus E is the projection W2 along W1, right? W2 along W1, right? Now let E be the projection on W1 along W2. On W1 along W2. Here direct sum condition satisfying, B equal to W1 direct sum W2. We will write this one W2 direct sum W1 is okay, both are same, okay. W2 direct sum of W1. Let alpha equal alpha 1 plus alpha 2 belong to V, where alpha 1 belong to W1, comma alpha 2 belong to W2. Okay. By the definition of projection, we have E alpha equal to alpha 1. Now we consider this one I minus E alpha. I minus E alpha equal I of alpha minus E of alpha. I of alpha because identity mapping alpha minus alpha 1. Alpha minus alpha 1 becomes alpha 2. Right? Alpha minus alpha 1 becomes alpha 2. Here I minus E alpha 2. Suppose E alpha equal alpha 1 means E is the projection W1 along W2. Here E minus alpha equal alpha 2. Therefore, I minus E is a projection along W2 because alpha 2 belongs to W2 no along W2 along alpha minus I minus E is a projection W2 along W1. Okay, W2 along W1. Therefore, I minus E is a projection on W2 along W1. Okay, these are the part very important to here, right? W2 along W1. Okay.